Hello everyone, in this video we are going to study this expression 3 to the power 2 to the power 1 minus x square, and where x is any real number, and this expression turns out to be really tricky. Okay, why we'll see. And the question here is, for how many values of x this expression gives you integer numbers. Okay, there are some obvious guesses for x. You can obviously see some values of x for which this gives you integers, but those are not all. Actually, there are some other tricky values for x for which this expression gives you integers, and there are many actually. Okay, so that is what is the purpose of doing this video. Well, so let us start with the question 3 to the power 2 to the power 1 minus x square. The question is which integral values it can take. Okay, and then how many such x values are there for which these integral values are taken. The question is very obvious. One easy guess, you can observe this. One easy observation is that x equals 0 gives you an integer. How? Okay, if x equals 0, then the expression is 3 to the power 2 to the power 1 minus 0. That gives 3 to the power 2 to the power 1, and that is nothing but 3 squared, and that is 9, which is an integer number. Another observation you can make here is that x equals 1 also gives you an integer. How? 3 to the power 2 to the 1 minus 1 for x equal to 1 gives you 3 to the power 2 to the power 0, and 2 to the power 0 is 1, so 3 to the power 1, which is 3, an integer value. Okay, so for x equal to 0 and x equal to 1, this gives this expression gives integer values. Okay, are they all? That is the vital question here. That is the main focus here. Okay, you can also make another observation that 3 to the power 2 to the power 1 minus x square cannot take any negative value. Why is that so? Okay, if you take any capital X, this is capital X, not the small same x now. Okay, for any capital X which is bigger or equal to 0, what is 3 to the power x? That is always bigger than 0, because for capital X equals 0, 3 to the power 0 is 1. And if x is positive, 3 to the x is positive, there is no doubt. Therefore, for all x which are bigger or equal to 0, 3 to the power x is positive. Now, if x is negative, what happens? Okay, if x is negative, then 3 to the power x can be written as 1 by 3 power minus x, right? But if x is negative, minus x is positive, and 3 to the power minus x will then be positive, and 1 over some positive number is always positive, right? So for any x, you take x less than 0 or bigger than 0 or equals 0, 3 power x is always positive. And this same explanation applies to the 2 also, right? Not instead of basically instead of 3 power x, if I take 2 power x, that is also same, right? So for any x value here, 2 to the power 1 minus x squared is always positive, and therefore 3 to the power this is always positive. Therefore this exponential, any exponent cannot take negative values, that's all. So 3 to the power 2 to the power 1 minus x square cannot take negative values. If you just for example, if you want to see what happens when the power is negative, okay, I have taken 3 to the power minus 1.5, which is a negative number, so negative exponent is there, and then this expression can be also equivalently written as 1 over 3 to the power 1.5. Now you believe that 3 to the power 1.5 is positive, therefore 1 by a positive number is again positive. Okay, that's all. So 3 to the power 2 to the power 1 minus x square cannot be negative. Okay, so we have seen so far that this expression does take the values 3 and 9, and it cannot be negative. Okay, so if it is possible, it can take some other positive integer values. We'll see what it is. Okay, so now some calculation. Let's say for any, let's start with any real number x. Okay, for any real number x, we believe that x square is bigger or equal to 0 and strictly less than infinity. Okay, this is absolutely fine. Then what happens to minus x squared? So minus x squared is then bigger or equal to minus infinity, because we are doing minus here. Okay, and minus x square is always less than or equal to 0. So minus x squared cannot be positive, that's all, because x square is always positive for any real value of x. Okay, then what happens? Just add 1 to all these entries, all these numbers. Okay, so 1 minus infinity is not going to change, it is again minus infinity. This gives 1 minus x square, the middle term, and on the right 1 plus 0, which is 1. Okay, fine. Then we can do this 2 raised to power this. Okay, so basically raise all the numbers to the power 2. So then 2 to the power minus infinity you get here, and all these inequalities remain same, and it middle term becomes 2 to the power 1 minus x squared, and then this is less than equal to 2 to the power 1, which is 2. Nothing fancy here. Okay, so 2 to the power minus infinity, you can replace that by 0, and then 2 power 1 minus x square as it was, and then 2. Fine. So what we have achieved here is this: for any real number x, we have 0 less than 2 to the power, strictly less than 2 to the power 1 minus x square, and less than equal to 2. Absolutely fine. Then raise all these numbers to the power of 3. So 3 to the power 0 you get on the left, strictly less than 3 to the power 2 to the power 1 minus x square, the expression which we are playing with, and on the right you get 3 square. Okay, so 3 to the power 0 is 1. I am writing just the values, middle term as it was, and on the right you get 9. Okay, now for x equal to 0, we have seen that it takes this expression takes the value 9. So basically this expression, it is less than equal to 9, and it does take the value 9 for some x, which is precisely x equals 0. And then at x equal to 1, we have also seen that this expression takes the value 3. Okay, the question is, fine, this expression is always strictly bigger than 1, so it cannot be 1. Okay, and it does take the value 9. The question is how many such and basically whether this takes any in between values, any in between integral values here, like 2, 4, 6, 5, all these numbers are in between 1 and 9, whether this expression takes these values. Okay, so my claim is that 3 to the power 2 to the 1 minus x square also takes these values 2, 4, 5, 6, 7, 8. Basically the other integer numbers which are strictly bigger than 1, because this expression is always strictly bigger than 1 by this calculation. Okay, and it is less than equal to 9, and there are only these integers left. Okay, 2, 3 is we have seen that 3 values is taken, and 4, 5, 6, 7, 8, and 9 is also taken, right? Okay, so what about these remaining numbers? My claim is that this expression does take all these values. Okay, fine. So why? That can be explained by this very well celebrated theorem called the intermediate value theorem. What is that? We'll just see in a moment. Suppose you have a function fx defined on a closed interval ab to r. So basically this is a real valued function defined on ab. Suppose the function is continuous. Okay, and then suppose if a, the functional value at a is alpha, and if b is beta, then the intermediate value theorem says f takes all the values between alpha and beta, not only integral values, all the values between alpha and beta, and therefore the function, if it is continuous and defined on some interval ab, if a is some alpha, if b is some beta, then in particular all the integral values between alpha and beta are also taken. That is not a problem. Okay, so now what happens when x is very large? Okay, when x is very large, our expression tends to 1. Okay, because if x is very large, 1 minus x square is a very large number but negative, and 2 to the power that very large negative number will give you a value which is very close to 0. Then 3 to the power a value which is very close to 0 will give you a value which is very close to 1. That's all. Okay, but it is never 1, because this expression, the 3 to the power 2 to the power this number 2 to the power 1 minus x square can never be 0. Okay, we have seen that. Fine. And we have seen at x equal to 0, this expression takes the value 9. And this expression is actually a continuous function of x. There is no problem. For all x it is defined and so on. Okay, and therefore this is a continuous function which takes values very close to 1 and takes values very close to 9. Therefore all these values which are in between also taken by this expression. Okay, because just because of IVT this follows. Okay, intermediate value theorem, because this is continuous, this takes the value 9 and this takes values very close to 1, therefore this takes all the values in between, which means 2, 3, 4, 5, 6, 7, 8, 9. All these values are taken by this. This is the power of intermediate value theorem, and which will explain using graph. Okay, just hold on till then. Okay, fine. So another question which we'll ask here is this. Actually, this is the original question which was asked in the exam. Okay, you collect all those points. So basically we are constructing a set S. Okay, how it is constructed? S actually contains all the numbers x for which this expression is an integer. For example, 0 is already there. We know at 0 it is 3, and 1 is also there, right? Because at 0 the value is 9, and at 1 it is 3, right? So therefore 0 and 1, they are already there. What are the other values? We may not know, but we just want what? The cardinality of S. This is the actual question. Okay, how many such x values are there for which 3 to the power 2 to the power 1 minus x square is an integer? Okay, we still don't know how many such x are there. We only know what? That which integral values are taken. Okay, for example, for x equal to 1, the value 3 is taken, but we do not know whether some other values are also there for x for which the same value 3 is taken, right? Well, so we will actually explain this in the graph. Okay, this is the graph which I have drawn already, 3 to the power 2 to the 1 minus x squared, and this is the graph. Well, so you see the symmetry here. The graph is symmetric about the y-axis. Why? Because this function is actually an even function, right? For x and minus x, you will get the same values of the function, and that is the biggest observation here. Why? Because for even function, whatever value it takes on the left, it also takes values, the same value on the right. Okay. Now let us look at the graph. We proved that this is always less than equal to 9, right? Yeah, you can see it here. So this is 8, this is 10, and this is actually 9. Okay, you can just click it and check which value. Okay, we have proved that for x equal to 0 it is 9. It is already can be seen here also. Okay, that is the maximum value, and from 9 height it comes down. Okay, simply because the maximum value is 9, nothing else. Okay, now you see here that this is 0, this is 2, and this point is of course 1. So it seems like the curve is touching 1. Okay, for example, let's say minus 6 here. Okay, it seems that it is taking the value 1. We said it is strictly bigger than 1, right? But it is not the case actually. It does not take the value 1. If you close it, look, if you zoom in it, then this point we want to see. Okay, zoom in, and at some point you will see that there is a difference. We are still zooming in. Okay, and we must see. Okay, so here it is not visible. Actually the scale is very small, it is not going to that scale. Let me just go to home, and for example minus 4, if you see minus 4, it seems to be overlapping, but it is actually not. You see there is a gap here. Okay, and everywhere there will be gap because the function cannot take the value 1. Anyway, so now from here it is going up, right? Whether it takes 2 value, yes, here it takes 2 value. So basically the corresponding x here is here. Okay, some value in between 0 and minus 2, but this 2 value is taken on the right side also because the function is even, right? So for this x also, so for some x it is taking 2, it means for some minus x also it is taking 2, and vice versa. Okay, whether it is taking the value 3, yes, as long as it goes from 1, okay, from 1 to 9 there, okay, it crosses all these heights, and those are the functional values only. Therefore this expression takes all these values, like 2 is taken here, 3 is taken here. 3 we know already, this is at the value x equal to 1, right? And it is minus 1 actually. So on at 1 it is on the right, no problem. And then 4 it is taken, 5 it is taken, 6 it is taken, all the values are taken, and that is what intermediate value says. Okay, if the function is continuously moving, then somewhere it is very close to 1, and somewhere it is 9, here, so it has to take all the values in between. That's all. Intermediate value theorem on a graph is simply very simple to understand. Okay, so it takes all the values, but we also understand that at this point, at this negative x, it is taken 8. On the right also it is taken 8. Okay, so everything except 9, the values are taken twice, once at minus x, okay, and another time at plus x, because of the symmetry, because the function is even. Now going back to here, the calculation. So 3 to the power 2 to the 1 minus x square is taken, it takes the value 2, where it is achieved twice actually, at x and at minus x. That is what we have seen on the graph. And so is for other values like 3 to the 2 to the 1 minus x square, and then 3, 4, 5, 6, 7, 8. For all these, right? For all these, x and minus x, they are different. So how many total values? Total values are, so how many numbers? 2, 3, 4, 5, 6, 7, 8. There are 7 numbers. So 7 into 2 plus 1. Why plus 1? Because the 9 value is taken only once. Because at x equal to 0, the value is 9. And for x equal to 0, x and minus x, they are the same number, right? 0 only. Therefore, for 9, we have to take only 1. We get only 1 x, precisely x equal to 0. So 2 times 7 for all these values, twice for each. So 2 times 7 plus 1, which is 15. Okay, and that is the cardinality of the set S. So there are 15 x values for which this expression takes integer numbers. Okay, yeah, the video became lengthy, and that's all in this video. If you like the content, do press the like button and subscribe to our channel to motivate us. I sincerely thank you for watching this video.